Welcome. Let's talk determinants today. We're working pretty much under the assumption that you don't have a lot of background with determinants. So let's get started. Okay, first, I guess we should probably start even with a one by one determinant, but it's kind of boring. But if I had the determinant, or if I had a matrix 19, to talk about its determinant, we use more along the lines of what looks like an absolute value symbol. But this is a boring little one by one determinant. A one by one determinant is just equal to itself. So what is a determinant? A determinant is a number that associates to a matrix, a square matrix. So our square matrix 2 by 2 has some number that associates to it. It's not a code. So in other words, if I have a 2 by 2 matrix whose determinant is 74, if I'm told a 2 by 2 has a determinant of 74, I can't decode that and tell you the values. There's an infinite number of 2 by 2s that have a determinant of 74. However, there are some really neat applications with determinants. We are not getting into the applications today. Today is strictly mechanical. We're going to grind these things out. Okay, the process of finding a 2 by 2 determinant, the easiest process in my opinion. We'll talk about other processes later, but the easiest is we take the downward diagonal values, 3 times -8, and we subtract from that the upward diagonal products, 4 times -3. So the determinant of A, B, C, D, this 2 by 2, is just AD minus CB. Or in this case, -24 plus 12. -12 is this determinant. It's the value. It is a value that associates to that determinant. That determinant associates to -12, and there's some useful features for -12. Stay tuned. Watch our next video. Okay, let's talk about some other values. Now, there is a general process for finding determinants of any size. However, a 3 by 3 determinant, finding it, I believe, assume we're going to be talking about what are called minors and cofactors, but I believe finding a determinant, there's a special process, sort of like the 2 by 2, that allows us to find its determinant. I believe most people would steer toward it rather than minors and cofactors. So the process is, and eventually you won't have to do this part of it, but if you rewrite the first 2 columns, augment this with the first 2 columns, 2, 4, 4, just a repeat of column 1, repeat column 2, -1, 2, 2. What we look for here are our downward diagonals, the products right through here. That is, and I'm going to write this out longhand one time. So I get 2 times 2 times 1. Then I add to that my next downward diagonal, which is -1 times 1 times 4. And I add to that my other downward diagonal. And I get 0 times 4 times 2. I find those values. And I subtract from those my upward diagonals. My upward diagonals. 4 times 2 times 0 plus my next upward diagonal, 2 times 1 times 2 plus my final downward or upward diagonal, 1 times 4 times -1. So here we get 4 plus -4 plus 0 minus 0 plus 4 plus -4. I get 0. I get minus 0, which is kind of peculiar. That's certainly coincidental. They ended up being equal. But the determinant of this guy is 0. So here it is again. We take our downward diagonals and subtract from that the sum of our upward diagonal processes. Or diagonal products, I should say. We'll look at some other 3 by 3s so you realize, so I can make it really clear that this was coincidental. Perhaps not the greatest problem to show first, but the process is still there. All right. Find the determinant of the matrix by the method of expansion by cofactors. Wow, this is a spot right now where I think when we go through this, you're going to really appreciate that we're in an age of technology, graphing calculators. Expansion by cofactors is the process we must use if we are above a 3x3 system. And what expansion by cofactors says is that the determinant of a square matrix can be found by taking the entries from any row or column. So I could go row 1, I could go column 3, I could go row 3, it doesn't matter, and multiplying those by their corresponding cofactors. Of course, that should be a red light right now. Well, what in the world is a cofactor? Well, I'm just going to write this out. This wants us to find them by expansion of row 2. And we're going to actually turn around and do this another way as well. Again, if I was to be finding this determinant, I would use the process that we used in the last problem. But if we get bigger than a 3x3, we have to use expansion by cofactors. That process that we just looked at on the last slide will not work. Excuse me. Okay, so the determinant of this equals 6 times whatever 6's cofactor is, and we're going to call that C21 for cofactor row 2, column 1, plus 3 times its cofactor, that would be C22, plus 1, this guy, times its cofactor, that would be C23, row 2, column 3. So now we need to know what cofactors are. Excuse me as I clear my throat here. Okay, so cofactors are based on minors. So here's the deal on minors. I need to find my minor to go with cofactor 2-1. To find it, I need to find minor 2-1. To find minor 2-1, here is the process. I go to entry 2-1. I eliminate its row and its column. And the remaining determinant, what's left, is 4, 2, -7, -8. So now I have a simple little 2x2, which we learned is our downward product, 4 times -8, -32, minus our upward, -7 times 2, -14. So I end up with -18. That is minor 2-1. All right, let's move on and find our other minors that we need. To find cofactor 2-2, we need minor 2-2. And once I find all the minors, then we'll talk about how we get to cofactors. So minor 2-2, to get it, I go to my 2-2 location. A lot of times I'll just do this in pencil real lightly if I'm working with it. And I eliminate that. That leaves me to find the determinant -3, 2, 4, -8. Okay. And that is our downward diagonal, -3 times -8, 24, minus our upward diagonal, 4 times 2, 8, and I get 24 minus 8, 16. That is minor 2-2. Okay, to find minor 2-3, my value that's in 2-3 is this guy. I eliminate his row, could be her row, I suppose, and her column, and I am left with minor 2-3 is -3, 4, 4, -7. Downward diagonal, -3 times -7, 21, minus upward diagonal, 4 times 4, 16, and I get 5. Okay, now, cofactors are an absolute breeze. So cofactors, it's a strange rule for it, but it says this. It says cofactor, I'm going to use ij equals I plus, excuse me, that's not quite right, equals, in parentheses, negative 1 to the I plus jth power, which is weird, times minor ij. So what does this do to minor? Well, if I plus j has an even sum, if I and j have an even sum, then the negative gets absorbed and cofactor ij is just equal to minor ij. However, if my row plus my column, I plus j that we're dealing with, is an odd number, negative 1 to an odd number is negative 1 times my minor. So cofactor 2, 1 is either negative 18 or positive 18, depending upon the sum of these guys. 2 plus 1, 3. So that would be 3 negatives, making this negative, or the opposite of negative 18, positive 18. Isn't that strange? Okay, cofactor 2, 2 is either 16 or negative 16. However, 2 plus 2 is even. If I take negative 1 to the positive 4th power, that negative gets absorbed. So cofactor 2, 2 is the same as minor 2, 2. And similarly, cofactor 2, 3 is either 5 or negative 5, but since 2 plus 3 is 5 odd, it is the opposite of. Whew. All right, let me come back up here, create just a little bit of space for myself. Maybe I don't need it. Maybe we can get this done. So my result is 6 times cofactor 2, 1, 6 times 18, plus 3 times cofactor 2, 2, 16, plus 1 times negative 5. And now I definitely need to create some space here. We'll get rid of this cofactor rule. And now you could go to calculator, or 6 times 18, let's see, that's 60 and 48, 108 plus 48 minus 5, or 156 minus 5, 151. How is that compared to the downward diagonal idea? So we love that downward diagonal sum minus the upward diagonal sum that we just saw on the previous slide. I really prefer that for 3x3s, but do not fall into the trap to think that you can modify that for 4x4s and above. It will not work. Okay, so here's a case. What you'll notice on the next slide is we're going to be dealing with exactly the same matrix of values, finding their determinant. However, we're going to do that through a different row or column. So let's take a look. Hopefully we end up with 151. If not, we're going to start this video over. Okay, so same matrix. Now we are supposed to be using column 3. So column 3, by column 3, the determinant would be 2 times cofactor 1, 3, first row, third column, plus 1 times its cofactor, that's cofactor 2, 3, plus negative 8 times its cofactor, that's cofactor 3, 3. So what do we need? We need minor 1, 3 to find cofactor 1, 3. Minor 1, 3, here's 1, 3 right here. We need the determinant 6, 3, 4, negative 7, or downward diagonal negative 42 minus upward diagonal 12, and we get negative 54. Minor 2, 3, row 2, column 3. For that, I just take my eraser, come back up here, cancel, cancel. We are left with negative 3, 4, 4, negative 7, downward diagonal 21, upward diagonal 16, and result 5. Minor 3, 3. Erase my pencil marks, go to 3, 3, which is the negative 8. Eliminate. And we want negative 3, 4, 6, 3. Downward diagonal negative 9 minus upward diagonal 12, negative 21. So Done with that, but we need not minors, we need cofactors. Minors just get us to a spot where we can find cofactors. So cofactor 1, 3 is the same as minor 1, 3, except it's times negative 1 to the fourth. Negative 1 to the fourth is even, so negative 1 to the fourth is positive 1. So positive 1 times negative 54, negative 54. In other words, if the sum of row and column is even, our cofactor is our minor. Cofactor 2, 3 is either 5 or negative 5, but since 2 plus 3 is odd, opposite of the minor. And cofactor 3, 3 is either negative 21 or positive 21, but 3 and 3, 6 keeps it the same, negative 21. So here's our moment of truth here. We get 2 times negative 54 plus 1 times cofactor 2, 3, negative 5 plus negative 8 times negative 21, making me a little bit nervous. Let's see how this works out. Negative 108 minus 5 plus 168. How we doing there? We get negative 113 plus 168. Do I have a mistake here? And I end up with positive where is my mistake? Negative 8 times 3, 3, 168. Okay, I bet you guys were all screaming at me when I did this one right here. Let's go ahead, negative 9, the upward diagonal minus 24. Nice. Anybody can do this. Negative 9 minus 24, negative 33, which makes cofactor 3, 3 be negative 33. Let's give that another shot. Hope that didn't provide too much confusion. My apologies on that. Let's go up. So fix our cofactor 3, 3 to be negative 33 now. Making this 240 and 24, 264. Making this guy 264, making this 151, and you might be asking, how did he catch that error afterwards? And maybe this is a good thing. It was because I knew coming into this problem, let me go back to the previous slide, that we had a determinant for this matrix of 151. That is not to change between rows and columns, so we should be at 151 regardless. So there you have it. Appreciate your patience with me on that. Maybe you weren't patient. Maybe you were throwing things at me. I appreciate that too. Okay, let's move on here. Okay, now I think as you can see, the little process that we showed for a 3x3 on the second slide might be preferable to minors and to going through minors and cofactors. Again, that is special to 3x3. I cannot expand these first 3 columns. The same thing will not work. So here is the process, and this is where you're going to, again, want to hug your calculator and say thank you. Back in the Stone Ages, when I was doing these for high school and college work, we had to go through processes similar to this, and I always joke, not that I'm bitter about it, but we have better processes, but I'm still going to show you the process of this. So if I can use any row or any column, and I'm going to expand by minors and cofactors, I'm going to choose the column or row of least resistance. In this case, I like this guy, because the determinant of this would be 6 times its cofactor plus 3 times its cofactor plus 0 times its cofactor plus 0 times its cofactor, which means I don't really have to find those guys. So makes life a little bit better. So here's what we've got. I'm going to go find this guy's minor first. I'm going to eliminate its row. I'm going to eliminate its column, and I'm left to find minor 1, 3 is the determinant 2, 7, 6, 1, 5, 1, 3, 7, 7. And now that I'm down to a 3 by 3, I have options. And I could go through the minor cofactor thing again. I'm not going to. I'm going to do my downward diagonal. See if we can follow this. My first downward diagonal. 2 times 5 times 7, 70. Plus, my next one would go 7 to 1 to 3. 7 times 1 times 3, 21, plus my next one would be 6 times 1 times 7, 42, minus. Okay. I have to clear this out so I can put some new lines on this. If I was using a pencil, of course, I wouldn't have to do that, but let's go ahead and rewrite this. 2, 7, 6, 1, 5, 1, 3, 7, 7. Upward diagonal. 3 times 5 times 6, that is 90. Plus, how about this one? 7 to 1 to 2, 14. Plus, what's left? 7 to 1 to 7. 7 times 1 times 7, 49. Okay, so we end up with here 70, 21, 91, and 42, 133. Minus 90 and 14, 104 and 49, 153, we get negative 20. So if minor 1, 3 is negative 20, what is cofactor 1, 3? Well, cofactor 1, 3 is either negative 20 or 20, but these add up to an even, so it stays the same. So far I know that my determinant is 6 times negative 20. Let's find our next minor. So next, minor 2, 3. Minor 2, 3. Minor 2, 3. Entry 2, 3 is located right here. I'm going to ignore its row, its column, and I need to find the determinant of 2, 6, 2. 1, 5, 1, 3, 7, 7. My downward diagonals. Can you follow this? 2 times 5 times 7, 70. My upward, or my second downward diagonal could be 6, 1, and 3. 6 times 1 times 3 plus 18. My next downward diagonal could be 2 times 1 times 7 plus 14. Minus the sum of my upwards. 3 times 5 times 2, that is 30. The next one, 7 times 1 times 2, 14. And the final one, 7 times 1 times 6, 42. So I get 14 and 18, 32, and 70, 102. Minus, let's see, 14 and 42, 56, and 30, 86, for a value of 16. Is that right? I should have a calculator when I do this. That would help me. Okay, so the rest of mine is now plus 3 times cofactor 2, 3. Well, what is cofactor 2, 3? If this is minor 2, 3, cofactor 2, 3 is either 16 or negative 16, but 2 plus 3, 5 makes this negative. And I get negative 120 and minus 48 for a determinant of negative 168. A number that goes with that matrix, not unique. In other words, there's other 4 by 4 matrices that have a determinant of negative 168, but it's a number that has some applications for that. And that will be in tomorrow's video. Okay, so Pardon me for the error along the way. I don't think I'm going to remake this video in the next few days, so you're stuck with it. But once again, that's probably worthwhile for you to see. I wish I could have bluffed my way through it and said that I did that on purpose. But stay tuned. If you are just joining us and not a member of this class, and you just happened across this, you can find the lessons associated with this at purpleshirtednerd.com. This is chapter 7.7, and you might want to come back and check the 7.8 video that we put out. We may have an application or two to show you with that. Thanks for viewing.